Okay, so the last topic that we're going to talk about in this energy sort of chapter is the topic of power. And in physics, power is given the symbol P. It is the rate of energy transfer. So how quickly a given amount of energy is transferred from, say, one form to another or from one location to another. So let's just sort of do an example here. So suppose we've got a car which starts out at rest. So its kinetic energy initial is equal to 0. And the idea is, we step on the gas and we accelerate. Okay, and so in doing so, we are converting chemical energy in the gasoline into kinetic energy of the car. And so finally there's some kinetic energy in that car, which is, say, I don't know, just pick an easy number. It's a lot bigger than 1,000 joules, but let's say it's 1,000 joules. Okay, and so the car is moving, say, at highway speed at this point. Okay, and so there has been a transfer of kinetic energy from chemical to kinetic energy. There's been a transfer of energy from chemical to kinetic, and that transfer, the total amount of energy transferred, is final minus initial, is 1,000 joules. That's how much chemical energy you need to transfer into kinetic energy to get the car going at highway speed. Okay? Now, let's suppose that the time taken for the transfer is long. Okay, so you got a car that isn't very powerful. Okay, and so the time taken is, say, I don't know, let's say it takes 100 seconds for the car to get up to highway speed. So then the power involved, the rate at which energy is being transferred, is 1,000 joules is being transferred in 100 seconds. Okay, so joules per second is watts. 1,000 divided by 100 is 10 watts. So it's saying that the power of the car required to do that transfer of 1,000 joules in 100 seconds is a 10 watt powered car. Okay, it's like light bulbs, low power, high power. So, but suppose that we want to get up to highway speed. We want a higher performing car. We want to get up to highway speed not at 100 seconds. That's depressing. We'll aim for, let's say, 10 seconds. Okay, so then the power required is, well, we want to transfer 1,000 joules of energy into the kinetic energy of the car. And how quickly are we going to do it? Well, 10 times as fast as before. And so it's only going to be 10 seconds. So joules per second is watts. Okay, and so 1,000 divided by 10 is 100. Okay, and so in order to we end up at the same place. We end up with the car traveling on the highway at highway speed. But if the car is more powerful, 100 watts rather than 10 watts, we can get to that state of the transfer being done faster. Okay, so to get 0 to 60, so to speak, you need a more powerful car. Okay, so that's the basic idea of power, is we have a fixed amount of energy that we are going to transfer, and then the rate at which we can transfer that depends upon the power. How powerful the motor is. That will be the rate at which it can transform chemical energy into kinetic energy, and so on. Okay, so very good. So let's just sort of define this more formally and learn something a little bit about power that's kind of interesting. Okay, so the idea is power is the rate at which energy is being transferred. And so we're talking really about energy transfer mechanisms. So there's lots of ways of transferring energy. You have heat, a transfer of thermal energy. You have electromagnetic energy transfer with light, and so on and so forth. But the most common example of an energy transfer mechanism that we encounter in Physics 121 a lot is work, a force acting through a displacement. Okay, so the usual general picture is we have our object, which is moving in three-dimensional space somehow, and relative to some fixed origin point. Here we have, say, at initial time t, the position of our object. Maybe this is an airplane or something like that. The position of the object at time t is this. And then a short time later, so at a time t plus dt, where dt is a small interval of time, the airplane has moved from here to here. So that the new position is r at time t plus a small little infinitesimal time added to that. Okay, and so during that time dt, the plane moves from there to there. Its displacement is dr, is the difference between that vector, final and initial position vector. So that's dr. Okay, very great. Very good. And so remember that the velocity, and velocity is going to play an important role here, the velocity of an object is always tangential to the trajectory. It's in the direction of dr. Velocity is dr divided by dt, and so it's this vector rescaled by dt. So just the length is changed. Same direction as dr. So that's the velocity of the airplane or whatever it is, the object, at time t. Okay? And let's suppose that we are, while this airplane is in motion, there is a force acting on that airplane. And let's suppose that the force, I don't know, it doesn't matter, let's put it in this direction. So there's a force acting at that instant of time t. And what that force, well, I should make the force a little bit more in the direction of dr. That looks almost perpendicular to dr, and that isn't going to transfer any energy. So I think I got to put the label for dr down here, and then say the force is like that. So it certainly has a component of force in the direction of displacement. And so this force acting over the small time interval dt will transfer energy according to our energy transfer formula, the work done, which is F dot dr. Okay, so yeah, so W is the work done by the force F as it moves through displacement dr. It's also equal to the energy transfer. Energy transfer. Remember that work is an energy transfer mechanism. So it's the energy transferred to our airplane or whatever other objects in motion during time dt, I should say dt, not delta t. So it's an infinitesimal time interval, dt. Okay. And that work done is the vector dot product of the force at that instant of time, vector dot product with the displacement at that instant of time, dr dt. Okay? Very good. So we have transferred some energy to our system. Now power at this instant of time is the instantaneous rate at which the energy is being transferred. So the power at this instant of time, the rate at which the energy is being transferred to that airplane by that force is going to be the amount of energy transferred divided by how long. Rate of energy transfer is energy per unit time, joules per second. So it's the amount of energy transferred, which is work done, divided by how long it took. Okay? The shorter the time it takes to transfer that amount of work, the greater the power involved. Make the denominator smaller, then power becomes larger. Okay? Or a greater amount of energy transferred in the same amount of time means larger power. Okay? So now let's work this out. So the work, the energy transferred during that infinitesimal time interval dt is the force at that instant of time t, vector dot product with the displacement at that time t. And then we divide that whole thing by dt. So now what we're going to do is we're just going to collect this guy over here together. So it's the vector force, the instantaneous force vector at time t, and it's a vector dot product with the vector dr divided by dt, the scalar dt. Well, dr dt, well, that's just the velocity. And so that's the velocity at the instant of time t, the instantaneous velocity. So that is super important. So I'll just write this down then. So power at any instantaneous power is the instantaneous force, vector dot product, the velocity at that instant of time. Okay? So work, energy transferred, is force dot displacement. Power is force dot velocity, which is the rate of change of the position. Displacement divided by time. Okay? So force dot velocity, that's very important. That's what power is. And the dimensions for power are well, it's energy over time. Okay, energy transfer divided by time, energy over time. So it's joules per second are the units, and joules per second, that's the same thing as watts. Like a 100-watt light bulb means that that light bulb is converting 100 joules of electrical energy into thermal and light energy per second. Okay, 100 watts is 100 joules per second. More powerful light bulb means it's a higher rate at which it's transferring electrical energy or electromagnetic energy into other forms of energy. Light. Okay, very good. So I think that's the main point there. So now I want to give sort of two examples here. So one of these examples is an escalator or a conveyor belt. So the idea is you've got something like this. You've got a cylinder. This is the side view of a cylinder. And you have another cylinder up here. And then wrapping around these cylinders is a conveyor belt. Okay, and so it's a belt. It's like, think about these as pulleys. There's a little belt that goes around. And comes around like this. Okay, and the idea is what we're going to do is we're going to put a box, say down here, of mass m, and what we would like to do is raise this box up, okay, along that conveyor belt. And so the way we do that, and let's say the total distance d up this conveyor belt, the total distance up the conveyor belt is d. And the height of the conveyor belt, the height at the top compared to the bottom, we want to raise this box through a height h. Okay, there's also some horizontal displacement here, but we basically want to raise it a height h. Okay, and this angle here is theta. And what else do we need here? Well, so in order to do this, we are going to have to apply a twisting force, a torque, to this drum. Okay, and so we'll have to exert a twisting force, and so what we do is we have an electric motor. It's not a very good drawing of an electric motor. But anyways, there's an electric motor, and that electric motor is connected through an electrical plug into, an electrical power outlet. And so basically what we're doing is we are putting electrical power in here. Electrical power, measured in watts, so and so many joules per second. We're putting electrical power in here. This motor is converting that electrical power into mechanical power, okay, which there's a torque. There's a twisting force on this drum. Okay, and what that's going to do is it's going to put this belt, this is a belt material, some kind of a belt made of some material, and it's going to put that belt under some tension. Tension T like this. Okay, and then there's going to be static friction that keeps this mass from just sliding down, that keeps this mass at rest with respect to the moving conveyor belt. Okay, and that static friction acts on the mass m in that direction, and it has magnitude, of course, equal to the tension in that conveyor belt. Okay, and we're going to imagine that this mass is moving up the conveyor belt with a speed v, and we're going to make a simplifying assumption, but still it results in some interesting stuff, a simplifying assumption that the speed v of this mass as it moves up the conveyor belt is constant. Okay. What else do we need to say? I think that's basically it. Okay, and so we're going to need to know what the forces are acting on little m. We need a free body diagram of little m. So little m, there's forces acting on it in such a way that the speed is constant, the velocity is constant. So there are forces acting, and they better add up to 0 because there's no acceleration. Okay, so what are the forces acting? Well, as usual, there is the field force, the weight pulling down. Okay, so what do we want to call that? Let's call that mg. Okay, and there is a force of static friction because the block M is not sliding relative to this belt. Then if it were like frictionless, the block would just slide down. It's not sliding down, so there's no sliding happening. So it's a force of static friction that's keeping M from sliding relative to the belt. And that force of static friction is in that direction, opposing the sliding down. Okay, so that's up like this. There's a force of static friction in that direction, and that force of static friction is of the same magnitude as the tension force. So it's the same as the tension force in that pulley. If this pulley is under tension, it's like a rope that's under tension, that's attached to the mass. Okay, and so it's pulling up. Okay, so we have that, and the angle here is theta. Okay, because it's up the incline, up the pulley there. And what else? Oh, and of course the belt is exerting a normal force, okay, perpendicular to itself. So there's a normal force acting on the block. So these are the forces acting on the block. Now, because the velocity is constant, so there's no acceleration, it must be that all of these forces add up to 0. So, so one thing to say sort of immediately here is we can work out what the tension is. So because the velocity up the incline is constant, there can be no net force up the incline. Okay, and so let's see, what are the forces up the incline? Well, there's the tension pulling up the incline, and then there's a component of the weight which is pulling back like that. So the component of the weight pulling back must equal the tension. And so we can write this down, so we can just immediately solve for that. So the tension is going to be mg times, when theta goes to 0, that goes to 0, so times sine of theta. Right? So when we tilt this guy down like this, we tilt the incline down to horizontal, then the tension in that in that belt would go to 0. Okay, as we crank up the angle, the tension increases. Okay, which seems obvious, seems intuitive. Okay, so we've got that. That seems right. I just want to point out a couple of things here. So this is mg, and then what is sine theta? Well, sine theta, sine is opposite over hypotenuse. That's h, the height you want to raise this block through, divided by the hypotenuse d. So it's h divided by d. And so you recognize, well, what's mgh? Well, mgh, of course, is the change in the amount of energy stored in the gravitational field when the mass little m is raised from this point through a height h up to this point. Okay? And so that's the change in the energy stored in the gravitational field divided by d. Okay, so you have that. So there's a very important thing to sort of point out about this. I'm not going to run out of room here. The important point here is that the tension T here, so T, let's write it down here. So T depends on what? Well, I mean, G is just this, the constant gravitational field. In terms of the things that you can change, it depends upon the mass of the block that you're trying to raise up that conveyor belt. So it depends upon the mass, and of course it depends upon the angle theta, as we just said. So when theta is small, the tension will be small. As we increase theta, the tension gets larger. Also, if we double the mass, the tension also needs to double. So the tension depends upon the mass. So the tension depends upon mass, and it depends upon the angle theta. The point is, it does not depend upon the speed v. Now, you might find that a little bit odd. So this is kind of interesting. So what it says is, suppose you're moving this guy up at 1 meter per second, and then you say, oh, that's a little too slow. So then you want to accelerate it. You want to make it move up faster. So what you're going to do is you're going to crank up the electrical power a little bit, and you're going to exert more torque. The tension is going to increase. There's going to, so gravity, the force pulling back by gravity won't change, but you'll increase the tension a little bit. So there's a net force in that direction, causing this guy to accelerate, to pick up speed. Okay, and then you want it to now move at a constant higher speed. So it was 1 meter per second. and then you crank it up a bit, and then, now 2 meters per second. So during the time that you are accelerating it, well, the tension is going to increase, but then now that you're moving at a constant speed again, even though it's faster, the tension in that conveyor belt doesn't change. So whether you're moving it up slowly at a constant speed or quickly up at a constant speed, it's the same tension in that conveyor belt. That's kind of interesting. Okay, so now what we want to do is we say, suppose that we would like to raise this mass from down here up to here through this height h during a time delta t. That's the crucial thing. Power is the rate of energy transfer. Okay, the amount of energy transfer is, of course, delta U gravity. That's the amount of energy that we're transferring. And then we want to figure out, well, what is the time that takes? Shorter time will require a more powerful motor. Okay, this motor has some power P. Okay, so let's work this out. So the power that's required, okay, the rate at which electrical energy here needs to be converted into mechanical energy and so on and so forth, that power, so the rate at which energy is being transferred is going to be the force. It's the force, vector dot product with the velocity. Okay, and so it's the force acting on the mass times vector dot product with the velocity of the mass. Okay, so the force that's acting on the mass, well, that's the force of static friction, okay, but that is the same thing as the tension in that conveyor belt. So the magnitude of the force is just the tension, and the velocity is in the same direction, and it has a magnitude v just equal to its speed. And so the power, the rate at which energy is being transferred, is the tension in that conveyor belt times how fast you're moving this guy up. So obviously, if you double this, remember that t here, t depends on m and theta, but not v. Okay, so if we double v, then this thing doesn't change. If we double the speed, it requires twice the power. Because at the end of the day, you're just raising this thing up, so you're transferring some electrical energy here into gravitational field energy. And you're doing that transfer in a time delta t. And so if you move faster, the time it'll take to make that transfer is less. So if you double the speed of the conveyor belt, it's going to require a motor of exactly twice the power. Another way to think about that is this is the tension in the conveyor belt, and the speed is the distance d divided by the time delta t. So that's t times d divided by delta t. So another way to think about this is regardless of the speed, or t doesn't depend upon the speed, and d isn't changing here, so the power required is proportional to 1 over the time. So if it takes 10 seconds to go up, it requires a motor of a certain power. If you want to cut the time in half, raise it at twice the speed, delta t is cut in half, so the power required is twice as powerful of a motor. Another way to write this that's kind of instructive here is t. So what is t? So this is t times d over delta t. In fact, let me write it over here. So t we had was delta, the change in the gravitational field energy, divided by d. That's what t is. Multiplied by d over delta t. The d's cancel out. And so what we find is that the power can also be expressed as the total energy transferred. So basically, when you raise this mass from here to here, what you're doing is you're increasing the energy stored in the gravitational field. Where did that energy come from? Well, it came from this electrical energy pumped in here. Okay, so basically, the amount of energy transferred from electrical form to gravitational field form is the increase in the energy stored in the gravitational field. So that's mgh here. So that's delta U gravity. So basically the power, the rate at which energy being transferred is just delta UG divided by delta T. And so you can think of this conveyor belt with a mass stuck on it as this sort of fancy machine that basically converts electrical energy into gravitational field energy at a certain rate. Okay, so if you double the power of the motor, it will double the rate at which you're converting electrical energy into gravitational field energy. Okay, so that's kind of cool. Oh, one other thing I wanted to point out is that so power is equal to T, the tension, times V. And remember that this tension does not depend upon the speed V. So the idea is for a motor of fixed power, so suppose that the power is fixed. Okay, so we have only a 100-watt motor, okay, and we're like operating at maximum power. So the power, if the power is fixed, then if we double M, if we double the mass, so we've got a motor of fixed power, 100 watts, chugging away here, and it's raising a mass of, say, 100 kilograms at a certain speed, up like this. If we double the mass, stick another box on, identical box on, then what's going to happen, if we look at the tension, well, G won't change, sine theta won't change, but the tension will double because we've doubled the mass. So if we double the tension for a fixed power, we have to 1/2 the speed. Okay, so doubling M requires that we must cut V in half. Or equivalently, we must double the time, delta T, that it takes to travel through that fixed distance D. So if I've got this conveyor belt running, this motor running at full power, and it's going up, the mass is going up at a certain rate, speed V. If I stuck another box on there, then the two masses together will go up at exactly half the speed. Okay. So anyways, so that's some nice sort of simple example of this idea of power. So power is really important because it's not always just about the amount of energy that has been transferred, it's how quickly that energy has been transferred. The more quickly it needs to be transferred, the greater power is involved. You need a more powerful car, you need a more powerful motor, that kind of stuff. In fact, let me just do one quick example involving a car, because I've mentioned the car a number of times. And this is actually a really nice example. So I started out with the car example. Now let me just formalize that a little bit, because it's something that you've all experienced and might not have really sort of put your finger on. And so now, with a bit of an understanding of power, you can sort of see why this kind of weird thing is happening. Okay. It's a little bit of a pain to wipe off this light quartz pen. There you go. Good enough. Okay, so car. Okay, so we've got a car, and this car is on a road. Okay, like that. And the idea, and this car has some mass m, and this car is moving with some speed v along the road here. And the idea is we are going to consider that this car is accelerating. Okay, so what does that mean? Well, what it means is in order to accelerate, there needs to be some net force. We're ignoring all friction here, all air resistance and everything, and we're going to say, well, in order to make this car speed up, we have to exert a force. And how do we do that? Well, we have an engine which creates a torque. And so there's a twisting force on this, say it's a back wheel drive, there's a twisting force. And so it takes that piece of rubber and tries to push it this way, but that rubber is in contact with the road, pushes the atoms of the road that way, so the atoms of the road push back that way, they spring back. Okay, and so there's a force that the road exerts on the car. So a force in that direction, and that causes an acceleration of the car. So not only has it a velocity, but there's an acceleration, which is equal to the force acting on the car divided by its mass. Okay, very good. So we got that. What else? Okay, so now we say, but now just a minute, power. So energy is force dot displacement. Power is force dot velocity. Always keep that in mind. Force dot velocity. Okay, so power. So the force is in that direction, the velocity is in that direction. The dot product is just the force times the speed. Okay, so we have that. But then we also know, according to Newtonian dynamics, that the force is the mass times the acceleration. So it's mass times acceleration times the speed of the car. So this is an interesting relationship. Okay, so this is a relationship between the acceleration of the car, we just ignore m here, it's a constant. There's a relationship in the acceleration of the car, the speed of the car, and the power of the engine. The power, the rate at which that engine is converting chemical energy into kinetic energy of the car. Okay? Great. So let's look at this relationship because it's kind of really interesting. So suppose that your car has a fixed power, like we did here. This motor has a fixed power here, and we talked a little bit about that. Suppose that your car has a fixed power. Now, of course, the power isn't fixed, because when the gas is when your gas pedal is a little bit down, the engine is operating at a certain power level. When you put your foot pedal to the floor, well, then the power is larger. Let's suppose that we're talking about maximum power. Okay, so you're always trying to get this car to accelerate as fast as possible. Okay, so you got the pedal to the metal all the time. So P here refers to like maximum power. And suppose that that maximum power is fixed. There's nothing we can do about it, which is usually the case. It's just, we got just one engine here. Okay, we can't do anything about it. Okay, so we've got this this fixed power, and so we can think of the power in this equation as being a constant. Nothing we can do about it. And so what we want to do is look at, well, what is the acceleration then? So the acceleration then, when we solve for the acceleration, it's this fixed power P divided by mass times the speed. And so this is a constant, that's a constant, and so it's proportional to 1 over v. Acceleration of the car under like maximum power, pedal to the metal, is proportional to 1 over the speed, roughly. We're ignoring lots of complications, okay? So what does that look like? So here's the acceleration as a function of the speed of the car. Okay, so a 1 over v curve looks like this. Okay, and so what we see is for slow speeds, okay, we see large acceleration. Okay, so when you're just starting, say at the stop sign or whatever, you press the pedal to the metal and you really feel the car accelerating. Okay, but now if we're moving at high speed, we're on the highway now, going 100 kilometers per hour, so we're moving at high speed, then the acceleration available is small. So it's small acceleration. And I'm sure you've all noticed this. So you're on the highway and you're trying to pass somebody, right? And so, you get into the passing lane, you put the pedal to the metal and it's like, right? And just doesn't like pick up speed nearly as fast as, nearly as greatly as you experience like off the line, right? And so that's explained just by this idea of power. Right. Okay, so another way to say this same thing is, let's suppose that we wanted to feel that same acceleration that we feel off the line when we put pedal to the metal when we're moving really fast on the highway. Okay, what would that require? So suppose that we want the acceleration A to be fixed. Okay, we want that to be constant. So what does that imply? So now in this formula here, m and a are fixed, and so we'll solve for the required power. So then the power is equal to, well, we have it already, so there's this fixed constant, ma, because a is fixed, times the speed. So it's telling you that the power required will be proportional to the speed. Okay, so this is very different. So let me put this picture down here. So the picture associated with this graph, power is proportional to v, looks like this. Power is proportional to v, so it looks something like that. So what this is saying is that for slow speed, so if you're moving slowly, then it requires, in order to produce a fixed acceleration, I can feel myself being, pushed back into the seat, so to speak, when I'm going slowly, okay, then that requires a low power. Okay, so low power. If I'm moving on the highway at high speed, so the speed is high, then in order to feel that same acceleration, fixed A, that I feel when the car's going slow, it requires a high power. Okay? And so because your power is basically fixed, the maximum power is basically fixed, in the real world it looks like this. It doesn't look like this. You can't just crank up the power like that. So, so let's try to understand this a little bit, why that's actually happening. So we're going to look at slow versus high speed. So I just want you to sort of feel this intuitively. So suppose we're moving at slow speed. Okay, so that means that during a time delta t, your car is going to move from, say, this location. It's going to move, it's because it's moving slowly, during some time it'll move only a little ways. Okay, so the delta x displacement is going to be small. Let me write that down here. So we just spaced issue on this board. So we have a small, because it's slow speed, during a time delta t, we have a small displacement. Okay, but during that time, we have a fixed amount of force being applied. Because to say that the acceleration is fixed is the same thing, because acceleration is force over mass. To say that the acceleration is fixed, it means that the force is also fixed. So what you're saying is, I would like to be able to, I'd like the engine, I'd like the, the torque and so on, so the force that exerts a road, the force that the road exerts on the car to be constant. Okay, what's required to make that happen? Well, okay, so for a fixed force here, a small delta x means that we have a small f delta x, relatively speaking. Now let's compare to the other situation where we're moving at high speed. Okay, so now we'll see the difference. So at high speed, during the same, 1 second, the same amount of time delta t, your car might have started over here, but because it's moving faster, during the same amount of time, it will have covered more distance. It will have been displaced a greater distance. Okay, so you have a large, at high speed, during a time delta t, you have a large delta x. Okay, and so, but you have the same f. It's important. Okay, you want the same acceleration, you need the same force. Okay, so to be able to apply the same force, you're applying that same force for over a larger displacement. Okay, and so that means that because delta x is larger, even though f is the same, you're going to have a large f delta x. Okay, and so, so what's just going on here is, when the car is moving slowly, then during that time delta t, the amount of energy that needs to be transferred from chemical energy in the gasoline to kinetic energy in the car, that transfer f delta x is small. Okay, so a small transfer in some time delta t is a small power, okay, low power. But now when we're moving at high speed, then to apply the same force, the amount of work done, the amount of energy transferred is larger. F delta x is now larger because delta x is larger because the car is moving faster. Okay, and so now we have a large amount of energy being transferred in the same amount of time. So it's a larger power, larger rate of energy transfer, larger power. Okay. So anyways, yeah, that's really all I wanted to say about that. So, so that's kind of cool. So power, it's not just about energy transfer, it's the rate at which energy is being transferred. That's a really, really important thing for all kinds of stuff. All the way from, machinery around the world to, astrophysics and explosions and rates at which energy is released during I should say, just came to mind. So, talking about power. So, so the most powerful event ever observed in human history is just the last couple of years, gravitational waves were discovered, and so I'm sure that all of you know that. So basically, these it was binary black holes, about 30 solar masses each or whatever, which coalesced into a single black hole, and in that process, 3 solar masses worth of energy was released. Okay, so the energy, we know that energy E equals mc squared. So the mass involved here, or delta E, is equal to delta mc squared. The change in mass, rest mass of the system, was 3 times the mass of the sun. So take something 3 times the mass of the sun times c squared, which is 10 to the 17. That is an enormous amount of energy has been released. Now, if that enormous amount of energy was released over a long time, like a million years, no big deal. Okay, but this was released in a very short time. It was released in about, I can't remember, I think it's about 1/10 of a second or something like that. But anyway, so you take that huge amount of energy divided by the 1/10 of a second it took to release it, you have an enormous amount of power. Okay, and like I said, this was the most powerful event that humans have ever observed. Okay, the rate at which energy was being transferred into gravitational wave energy was, it turns out, if you look at the power, stars have a luminosity, a power, watts. Okay, if you look at all of the stars in the observable universe, okay, the sun radiates at a certain wattage, like a big high-power watt light bulb. Now multiply that by like all the stars in the entire universe. So there's a lot of power, there's a lot of energy being, radiated by stars. And so it turns out that the power, the rate at which energy was being transferred into gravitational wave energy in this coalescing black hole was greater than the power of all of the stars in the observable universe combined. It was a brighter event than in gravitational waves than all of the stars in the observable universe combined. Okay, so that's a great example of a super high power event. Okay, so anyways, power is a really important concept. All right, very good.